This conference will now be recorded.
Hello everyone. We are continuing with chemical properties of aromatic amines, and there are total 7 types, and we are at the last type, which is electrophilic substitution, which we have already started. That is the initial information about the electrophilic substitution. Under this type there are 2 to 3 types, and the first one among these is nitration. Okay, so nitration, we get these 3 types of products, ortho, meta, para, that we have already seen in the last class. And among these, para is the major, 51%, then meta is the second major, 47%, and ortho, it is having very low yield, and that is because of the steric factor. And as NH2, it is orthopara orienting, so we should expect only these two. But actually what happens when there is presence of H plus, that is as we are using acidic condition, so because of that acidic condition, now what will happen? Aniline, it will be converted to anilinium ion. That means now it will remain in this form, protonated form. Now when it is protonated form, it is no longer orthopara orienting. Now it will be giving some meta oriented product also. So that is the reason significant amount of meta nitroaniline is also produced. So para and ortho product we are getting from the normal form of aniline, simply NH2 attached to pH ring. But meta nitroaniline we are getting from this protonated form of aniline, and the name of this is anilinium ion, because the condition is that we are using for this reaction concentrated HNO3 and H2SO4. This mixture, it is the reason why the medium is acidic in nature. So this is the nature of product that we get after nitration. This is the first example of this, remember, electrophilic substitution. Now the second method is basically, now we will see what are the other electrophile we can use. Fine. Now in this case, that is, see, we have taken amine, right? And we have also taken CH3COCl, that is the one reagent you can use for the insertion of this group. Another reagent also you can use, there is mention of OR, which is acetic anhydride, CH3CO, then OCOCH2. And after that, we have to, that is, if we want to get back from amide to amine, so there is equilibrium sign, you have to use any of these two reagents when you are moving from aniline to this amide. So NH2 group, now it is converted to NaCOCH3, and you can say as if it is protection of NH2 group. So to get the para product, if we want to get the para product in major amount, then NH2 group must be protected by acetylation, and for that purpose you can use acid chloride. In this case we have taken CH3COCl, or you can use acetic anhydride, and amide we are getting. And after this reaction, if you again deprotect NH2 group from NHCOCH3 form, that is this form, if you want to change to NH2 group again, then you have to use hydrolysis condition, either acidic or alkaline, and obviously heat. Here, why we are doing this type of protection? The reason is when there is simple NH2 group, then the lone pair availability over nitrogen, and when it is NaCOCH3, now the lone pair availability over nitrogen, that factor we have to consider. So when it is free NH2 group, that is initially, now this lone pair, it can take part in resonance with the double bonds of benzene ring, and that we have already seen. But when it is NHCOCH3, now another type of resonance is also possible, which is not towards benzene ring side, but it is towards the other side. Just follow the right hand side arrow. Here it is taking part in resonance, that is the double bond lone pair of electron that is present over NH, that is making NC double bond, and as a result there is now negative charge over oxygen. So this type of resonance is also possible. Now when this type of resonance is possible, the electron density donation towards benzene ring, that is now reduced, because now the resonance is occurring towards other side. So that is the purpose why we are doing this acetylation of NH2 group, because once you do this acetylation, now the molecule that you are getting, which is basically amide, and when amide, NaCOCH3, amide is basically the general name for this type of compound, where you will have NHCO group, but actually the name of this molecule is acetanilide. Now under this condition, if you use HNO3 H2SO4 mixture, which is nitrating mixture, right? Now you will be getting para-nitroacetanilide. Why it is so? Because now first of all the size is very large, so obviously para will be preferred. Another reason is the lone pair, it is taking part in resonance with COCH2 group, not with benzene ring. That means it is not making the benzene ring very activated, unlike the situation when it is free NH2. So that is why the chance of getting ortho para both that will be reduced. Only para we will get mainly, and after that again we have to get back to the free NH2 form. So that is why we are using hydrolysis condition. So the nitrated product is hydrolyzed to form the actual product. That is, if your purpose is to get only para-nitroaniline, not any other, then we can use this method. So in this way, nitration reaction basically we are controlling, isn't it? And so that it is our major product. Because in the previous case you have seen when there is no protection we have done, we are getting the mixture of all these three. So this type of acetylation you will observe not only in case of nitration, but it is also possible in case of bromination. Now first we will see this bromination example. In this case, the electrophile is Br+. Remember we are discussing electrophilic substitution. That means some electrophile will come towards aniline, that is aromatic amine, and any of this hydrogen at orthometapara that will be replaced by Br. Now, when you are using bromine water at room temperature condition, RT, room temperature, that means around 25 degrees centigrade. Now, what type of product you will get? You will get 5 ppt of 2,4,6 trinitroaniline. So here both ortho position and the para position, all these positions are there is electrophilic substitution. That means all these three hydrogens now they are replaced by Br, isn't it? Now, why we are getting tri-substitution? Because NH2 group, its donating effect is so high. It is so good donating group. So that is the reason now benzene ring is highly activated. So benzene ring here is basically nucleophile and electrophile is generated from bromine molecule itself. So when nucleophile is highly electron rich, obviously 3 times the substitution is occurring. But if you want to reduce this electron donating effect of NH2 group, so that now it will be also behave as nucleophile but not so nucleophilic. That means you are controlling. Instead of getting tri-substitution, suppose you want to get mono-substitution. So in this case, you have to again do this same thing that we have seen in the previous slide. We have taken aniline, then in presence of acetic acid and pyridine, we are getting this type of group NHCOCH3. One of the H is replaced by COCH3, and here byproduct is actually acetic acid. That is why pyridine is used, because pyridine will consume the side product. As a result, equilibrium will be shifted from left to right, and then we are using bromine in acetic acid. See the difference. In the previous case, when it is tri-substitution, you are doing it at room temperature and you are using bromine in water, but now we are using bromine in acetic acid. So reagent, it is not exactly same. Previous case bromine in water medium, now it is in acetic acid medium. So this acetanilide, it can also be called N-phenylethanamide. Now there is only para substitution. No, that is ortho positions, these two hydrogens are intact. So the reason is, first of all, obviously there is some steric factor involved. Compared to NH2 group, now you have NHCOCH3, which is obviously large. Another reason is also the electronic factor. Now the benzene ring is not so activated. That is, compared to aniline, in acetanilide, the benzene ring is not so activated. So that is why you are getting mono substitution, not tri substitution. And now this will be the final product. So if you want to do bromination, it depends on what kind of reagent combination or that is other reaction conditions you are using. Depending on that, you can get either mono substitution or tri substitution. Both are possible. Sulfonation. Now when we are talking about sulfonation, now the electrophile is SO3H, which is basically generated from H2SO4. Aniline reacts with concentrated H2SO4 and it forms anilinium hydrogen sulfate. And when we are heating it with H2SO4 at 453 to 473 Kelvin, so just subtract 273, you can understand in terms of degree centigrade, it will be around 200 degree centigrade something. So it is quite high temperature. And what we are getting? We are getting para-aminobenzene sulfonic acid. So NH2 group will be there, SO3H group will be there, but they will be para to each other. So you are not getting the final product directly. First, there is as the protonation of this NH2. So when look at the molecule H2SO4, as if one H is now with NH3, so that is why it is NH3 plus. And if you remove one H from H2SO4, I am trying to say you can write H2SO4 like this as if they are dissociated. So H plus is now with NH3 and this is the counter ion HSO4 minus. So this is acetanilide hydrogen sulfate. Now in presence of HNO3, what will happen? There will be, actually it will be HNO3, fine, not H2SO4. So after that what will happen? There is SO3H group which is now at para position. So this HSO4, from this SO3H will be generated and that will come in this position. So as if this hydrogen which is present at para position, now it will be replaced by SO3H. Okay. And this molecule is known as sulfanilic acid because this is also acid. It is not that only when CO2H group is there and we call it acid, but SO3H group is also when present, you can call it acid. And this molecule is known as sulfanilic acid. So sometimes remembering these names are important because if you are getting any problem where sulfanilic acid is mentioned, it is not mentioned that 4-amino sulfonic acid. Suppose it is not mentioned in that way, it is simply mentioned sulfanilic acid. So you have to understand what is the structure of sulfanilic acid. So it is para position NH2 group, and I mean at 1 and 4 position there is NH2 group and SO3H. But actually they, this molecule do not remain in this way. Here what happens, as this is basic group and this is acidic, so they will prefer to remain in zwitterionic form. Zwitterionic form means as if there is hydrogen exchange. So this H now it will be remaining with, this is actually NH3 plus. So it will be remaining with NH2 group. So this H, if it is removed from SO3H, now it will be SO3 minus. And now it is attached to NH2. It is protonated, so it is positive. So this type of ion, where both positive and negative charge is present together, and overall it is neutral. We call it zwitterion. Sorry. It will take place directly. You don't have to add any H2, HNO3. Okay. So this is the sulfonation reaction. Here electrophile, remember, electrophile is SO3H plus because this group is ultimately inserted in the para position with respect to NH2. So that is all about these 3 examples of electrophilic reaction. Now come to this one extra information, because when we discuss electrophilic substitution, I mean in aromatic ring, one important reaction is Friedel-Crafts alkylation as well as acetylation. Now you can, that is one question may arise in your mind, that why not for aniline Friedel-Crafts reaction not possible. So Friedel-Crafts reaction, though it is very important example of electrophilic substitution, but remember this reaction is not possible with aniline, and the reason is when we do this reaction we use AlCl3, which is basically the Lewis acid catalyst. This is important. Now when it is aniline, what happens? Lewis acid means it will have, it is electron deficient itself. That means it will, this type of molecule, they will be attracted towards electron dense region. And in aniline, this lone pair which is present over N, that is the electron dense region. So obviously there will be some interaction. And this lone pair of nitrogen, that will be donated towards AlCl3 because it is Lewis acid catalyst. It is Lewis acid, that means it is, its octet is not complete. It has some tendency to capture electron density. So now this lone pair will be donated and as a result there will be some positive charge over nitrogen. Now once the nitrogen is becoming positive because of this type of complex formation, you can also write it like this: NH2AlCl3 together, but now N because of this extra bond with AlCl3 it will be positive, and as it is acquiring positive charge, you cannot expect it as a very good electron donating group. Now when it is free NH2, it is very very good electron donating group. That is why benzene ring is activated, you can do electrophilic reaction. But if it is acquiring some positive charge, now its electron donating capacity is lost. Now the benzene ring is not so electron dense, and as a result Friedel cap reaction is not possible. But if you are thinking that why not to avoid LCLT, but you also cannot avoid that, but that is necessary for Friedel cap reaction for some other reason. So you cannot avoid LCL3 in Friedel cap, you have to use it, but when you use it, then the problem is there will be some positive charge generation over nitrogen in aniline molecule, and that is the reason ultimately we cannot do this reaction. And in Friedel cap reaction, basically in general, if I write what we actually do, suppose there is any R group which is donating, we use some Rx, that is alkyl halide, when it is alkylation. If it is acetylation, we use RCOCl, and obviously some Lewis acid, mostly LCL3. There is other Lewis acid also present, mostly LCL3. And what happens? This is R prime because already we have used R. Now, as it is orthopara orienting, this electrophile which will be generated from Rx, which electrophile will be generated? Now the electrophile is basically alkyl group, and when it is RCOCl, the electrophile is RCO plus. So this electrophile, it should be, that is ideally it should be inserted at any ortho position or para position. That is actually Friedel cap alkylation and acetylation. But remember, these are, it must be very good donating capacity, but when you are using LCLT, donating capacity is lost. That is why now it is becoming strong deactivated group, and further reaction not possible. So chemical reactions of aromatic amines are done. Basically in this chapter all the topics we have completed. So now we will discuss some problems, and these problems that will be regarding the whole chapter. Mostly we will see aromatic amine problem, because in this chapter mostly the problems that we will get, most of them are related to aromatic amine. In this question, it is asking that the correct stability order for the following diazonium salt. Now, when we are saying diazonium salt, it is basically this type of group. Cl minus is there, but there may be any other counter diazonium salt. So, what is the difference between these four molecules? In the first case, you have donating group at para position, then electron withdrawing group at para position in case of second molecule. Then in case of third molecule, there is no group, simply H, and in D, there is CN group present, cyano. This is also electron withdrawing, but remember it is not so withdrawing like NO2. NO2 is the most electron withdrawing. Now it is asking stability order. If you look at these four molecules, what is the region which is common for all? Obviously, it is the N2 plus Cl minus region, isn't it? And it is positively charged. That means the positively charged N2, which is attached to benzene ring, this part is electron deficient region. Now, as it is electron deficient region, and if there are some other groups present in the benzene ring, if it is electron donating, obviously now stability will be high. As OCH3 group is donating, this donating group, this is withdrawing group, and H is nothing. Cn is also electron withdrawing, but remember, compared to NO2, its electron withdrawing capacity is not so high. But obviously, we have to consider that the first molecule is, it should be maximum stable, because the positive charge over nitrogen, it is somehow balanced by the OCH3. If you want to draw resonance structure, that is also possible. So suppose I am writing N triple bond N. This nitrogen is positively charged. Now there is OCH3 group present here. If it is playing donating role through this lone pair, now what will happen? So the new structure that you are getting down, it should be something like this. Double bond, then OCH3, negative charge over this terminal nitrogen, positive this oxygen. Okay, so because of this type of resonance, now this molecule is very stable. But if there is electron withdrawing group, obviously stability will decrease. So A should be maximum stable. After that, B, C, D will come. So if you consider simply this fact, obviously you can easily remove these two options, because at a extreme position, highest position, there is C, but C cannot be highest. It should be A. And after A, in first option there is B, C, D. In second option there is C, D, B. So after A, the next molecule, is it B or C? That we have to check. Now obviously NO2 group is electron withdrawing, but H is not electron withdrawing. So after A, we can expect it should be C. And once you reach this logic, you can easily eliminate option 1, and that is why this should be the correct option. Okay. So when we already know among all these molecules only OMe group is donating. So these two will be cancelled. Now you are left with two options, and A is at extreme highest. After that, it cannot be B, because B is electron withdrawing group. How it will destabilize the diazonium salt molecule? That is the logic, right? And also CN will destabilize, but not so like NO2. So that is why D is before B in the correct option. So first A, OMe, this is OMe, then H, then NO2, and then, sorry, not NO2. So this is the order. Next question, A and B, you have to find in this following reaction. So the starting material is aniline. What reagent you are using? You are using NaNO2HCl, and we know this is diazotization reagent, because these two reagent together, they produces NaNO2. They produces HNO2, nitrous acid, and in presence of HNO2, the fate of aniline is now it is converted to diazonium salt. But remember, in this single arrow, there is another reagent which is KCl. That means once it is N2 plus Cl minus, in presence of KCl, it will be replaced by Cn. So molecule A, it is actually cyanobenzene. It cannot be remaining in N2 plus Cl minus form, because don't overlook this reagent, because as KCN is present, A cannot be diazonium salt. And if A is not diazonium salt, these two options cannot be correct, right? So now you are left with option 3 and 4. Next, what reagent you are using? You are using SnCl2 acidic condition H3O plus. And in this reaction, the fate of CN is now it is converted to CHO, and this reaction is known as, it is name reaction, which is Stephen reduction. In Stephen reduction, CN group is converted to CHO in presence of acidic water medium, SnCl2 and HCl. So that is why the correct option, it should be option, correct option, it should be option 3. This is A, cyanobenzene, this is B. And remember, even if you do not know Stephen reduction, then also you can answer this question, because these two options we have already cancelled, right? And you are left with option 3 and 4. Now, if you are not able to understand that, this reagent, it is basically which group will be produced. But at least this much information you know, that for synthesis of chlorobenzene, we do not use this type of reagent. Normally we use chlorine in presence of I mean to say chlorine gas in presence of some catalyst. Okay, so that information also can help you to choose the correct option, because if chlorobenzene is not produced, obviously now only one option is left, which is option 3. Next question, the diazonium salt of which of the following compounds? You have total 4 compounds and it is asking the diazonium salt of which of these compounds will form a color dye when it is treated with beta-naphthol. So when we have discussed diazonium salt in detail, in that part, this information is given in detail. Now, diazonium salt of which of the following compounds? Remember, this type of dye formation, it occurs through the formation of diazonium salt. And diazonium salt formation is possible only with aromatic amine, and it must be 1 degree. So it must be 1 degree amine and aromatic amine. Now, simply this information is enough to choose the correct option. Because if you look at option 1, this is not aromatic amine, it is methyl amine, pH, then CH2, then NH2. So obviously this is not correct option. Come to molecule number 2. This is not 1 degree. This is N with 3 groups. So this is 3 degree. It is aromatic, fine, but it is not 3 degree. It is also not fulfilling the condition. And number 4, this is 2 degree because 2 groups are present, pH and CH3. So this is also not 1 degree. It is aromatic but not 1 degree. So cross. Now you are left with only one option. So even if you can't remember the structure that you get from the bottle, but this much information is already given in the question, that diazonium salt of which of the following compounds. So diazonium salt you can produce only from option 3, which is 1 degree, as well as it is aromatic. So it is fulfilling all the condition. So this should be the correct option. Okay. But if you really interested to know what is actually going on, though it is already shown in diazonium salt slide. So this is the molecule which will be formed first. It is actually the diazonium salt, and this diazonium salt when treated with beta-naphthol. Beta-naphthol is naphthalene ring. These are the positions of naphthalene at 2 position, which is also called beta. So 1 position it is called alpha, 2 position beta. So at beta position you have OH. You can also call it 2-naphthol, but mostly it is called as beta-naphthol. So beta-naphthol, we know OH group, it is orthopara donating, and if you look at this position is actually ortho with respect to OH. So that is why this 1 position which is ortho position with respect to OH, there this diazonium salt part that will be attached. So this is a newly generated bond, and this molecule is dye compound. Dye means it is colored, intense color compound, and the color is scarlet red. Why it is intense color? Because we know when there is high amount of conjugation present in the molecule, you can see here benzene rings attached to each other through NN double bond. That means this double bond of left hand side, this benzene ring, it can take part in resonance through the double bonds of NN and the benzene naphthalene ring. So extended conjugation is present, and this extended conjugation is the reason why it is dye. Why it is so intense color. So this is the correct option. Next, considering the reaction, here a reaction is given. Aniline, you are getting X, then you are getting Y. So considering this reaction, you have to recognize X and Y respectively. Now we have 4 options, and in all these options, this is X, this is Y. So in this way, you have to choose. Aniline, what you are using? Very low temperature, 0 to 5 degree, NaO2Cl, which is actually it will produce HNO2. Now HNO2, that means X is nothing but diazonium salt. And when diazonium salt is treated with this amine, look at this, this is 3 degree amine, and this is NN dimethyl amine. And this type of group, it will increase the electron density in benzene ring. That means the para position of this benzene ring with respect to NME2 group, the para position is highly electron rich, and this electron rich region, it will be connected with the N2 plus. So just remember the previous equation. Here what you have seen. The ortho position with respect to OH, that is electron rich because of the donating effect of OH, and this electron rich position is actually attacking the terminal nitrogen of diazonium salt. So same thing is also happening here. In this case you have OH group, but in the next question now you have NME2 group, but both are playing analogous role. In the previous question OH is donating, but in this question NME2 group is donating. So ultimately the thing is same. If it is donating, now ortho position that is also electron rich, and para position that is also electron rich. So this is para position, this is ortho position. Okay. Now obviously the first molecule X major, it will be diazonium salt. So from that logic you can cancel 3 and 4 and look at molecule Y in option 1. It is at ortho position. So this newly generated bond is at ortho position with respect to NME2 group, but in option 2 it is at para position with respect to NME2 group. Now among these two obviously para will be preferred because of the steric reason. Because you are attaching a large group, obviously it will prefer the 4 position. Okay. So if I write it, in presence of NaNO2HCl, first there will be formation of N2 plus Cl minus. So this is molecule X. Then you are treating it with NME2 group, and this NME2 group from para position it will attack N2 plus Cl minus. Now if you really want to know how this is actually occurring, suppose I am writing N triple bond N, this is positive and Cl minus is the counter. Now the other molecule, that is the reagent in this case, NME2, right? This is benzene ring. Now how the reaction will take place, if you want to see the mechanism. So this para position now it is attacking and the other nitrogen is becoming neutral, right? So N double bond N. Now benzene ring aromaticity is lost. NME2 group, as it has taken part in resonance, it will be something like this, positively charged. And the other part, there is no change. Now what will happen? Aromaticity should be regained. So this H will be removed ultimately, that is minus H plus, and as a result, finally aromaticity in this ring will be regained. And what molecule you get? You will be ending up with this molecule. So this is option 2. The X is into pH N2 plus Cl minus, and this is Y. Three isomers A, B, and C. All these three, as we are calling them isomer, molecular formula is obvious. And the molecular formula is C8H11 nitrogen. So 8 carbon, 11 hydrogen, and nitrogen. Now among these three isomers, only A and C, you can do diazotization. Diazotization means you are using NaNO2HCl mixture, which will produce HNO2, and diazotization reaction will be there. Now as two isomer, two different compounds, you will get two diazotization product, P and Q. Now with this diazotization product, next what you are doing hydrolysis. Not just hydrolysis, you are also doing oxidation by KMnO4 acidic medium. And finally, you are getting product of A, that is P and Q. P may be from A or C, P may be from C, but finally from P and Q, the two products that you are getting after hydrolysis as well as oxidation, these two products, they are actually product of A, another is product of C. Now the another information is also there, R is having lower boiling point than S, and the isomer B, it is not giving any diazotization, but another reaction is mentioned here. Look at this molecule, PHSO2Cl. it is producing alkali insoluble product. Now PHSO2Cl, the reagent we use to differentiate 1 degree, 2 degree, 3 degree amine, because these three types of amine, when you treat it with this reagent PHSO2Cl, their behaviors are completely different, and that information helps us to identify whether the unknown amine sample, it is 1 degree, 2 degree or 3 degree. Now as it is mentioned alkali insoluble product, this information is actually will help you to understand what type of amine it is. Is it 2 degree, 3 degree or 1 degree? Now look at the options. In all options, you are having some NH2 group and some alkyl group, right? And in some options also you will see that is no alkyl group individual in benzene ring. I am trying to say here alkyl group is directly present in NH. So this is 1 degree amine. This is also 1 degree amine. This is 2 degree. Similarly, this is 1 degree. There is actually 2 alkyl groups. So this option cannot be correct because you must have 1 nitrogen. This cannot be the structure for ABC. So ABC respectively, that means the first molecule A, second one must be, this is C, like this. Now this alkali insoluble product, this information is the proof that it is 2 degree amine. Okay. So see, look at this blue colored box. Here this molecule, which is 2 degree molecule, when it amines, when you are treating it with Hinsberg reagent, that is PHSO2Cl, you are getting this type of compound where this H and Cl is removed and we get PHCH2, N, CH3 is still there, SO2PH. Now here we do not have any hydrogen that is attached to N, and that is the reason it is insoluble alkali. Suppose if it is 1 degree, there will be 1 alkyl group less and 1 H extra, and that H is attached to N, and that is the reason this H is acidic and it becomes soluble in alkali. But when it is 2 degree amine, Hinsberg reagent will produce compound which is insoluble in alkali. So B must be 2 degree. Okay. Now if B is 2 degree, what options may be correct? Because in option 2, this is also 2 degree. This is 2 degree. These two are actually same molecule. And option 3 also 2 degree, B. Now look at the other information. That is when you are treating A and C with diazotization reagent. So diazotization reagent, when we are applying, that means free NH2 group, 1 degree amine must be present. So here if you simply consider this orthoalkyl substituted aniline, now there will be N2 plus Cl. Now hydrolysis means you are treating it with water, you are simply heating the diazonium salt with water and you are simply heating it. So N2 plus Cl minus, that will be converted to OH. And KMNO for acidic condition, this is used for the conversion of, that is oxidation of the alkyl group. So whatever is the size of alkyl group, whether it is ET, propyl, methyl, always you will end up with only 1 carbon, and that carbon is CO2H carbon. So that is why we are getting finally OH and CO2H at 1 and 2 position. Fine. Now in this case, if this alkyl group is present at 4 position, same thing will happen, but now CO2H group will be at 4 position with respect to OH. So this is another possibility. Suppose this is C, this is 4 ethyl aniline. Same thing you are doing, N2 plus Cl minus produced. Actually Cl should be written like this. There is bond with nitrogen, not with Cl. Then H2O H plus, this N2 plus Cl minus is converted to H, and finally oxidizing reagent, it is converting this ethyl group. Same thing, same observation as you have seen in the first box you are getting. Now this is mentioned as R, this is mentioned as S. Why? Because of this information. It is saying that R has lower boiling point than S. So these two are basically isomer. I am trying to say R and S, these two are isomer, only the position is different. Now when it is ortho position, there is hydrogen bond possible which is intramolecular in nature. Suppose OH is there, COOH. So here hydrogen bond is possible between hydrogen and oxygen, and because of this intramolecular hydrogen bond, what will happen? The molecule, there will be no intermolecular hydrogen bond. Look at the spelling. Inter means hydrogen bond between two individual molecules, and intra means hydrogen bond within the single molecule. So in case of ortho, there will be intra. This is for ortho, but inter will be in case of para. So inter will be basically here. And when there is intermolecular hydrogen bond, because intra is not possible in case of ACE, they are far from each other. How intramolecular hydrogen bonding will take place? It will be obviously inter. And when it is inter, all the individual molecules, they are connected to each other, and boiling point will be high, because when you are converting them from liquid state to vapor state, you have to increase the distance between the molecules, and for that purpose you have to break those interactions, and so many different intermolecular hydrogen bond you have to break, and it will require very high temperature. So that is the reason when there is intramolecular hydrogen bond, I mean in case of R, the ortho molecule, in that case boiling point is low. But where you have intermolecular hydrogen bond, now the boiling point will be high. So this information will help you to understand that R is ortho and ACE is para. So because otherwise A and C, if you look at the options, both are actually 1 degree amine with some alkyl substituent. Fine. So that is the reason it is matching, all these informations are matching with option 2. And normally it is not meta. Because with meta, this type of information that R has lower boiling point than ACE, it is not applicable, right? Here also intramolecular hydrogen bond not possible, but intermolecular hydrogen bond also, whether it is possible or not, you cannot compare directly. It is mostly for para. So that is why this meta one also it is not possible. And also see, this meta structure is given in for the molecule A, and from A you are getting R, which is product of A. So, and it is having lower boiling point, but meta cannot have intramolecular hydrogen for meta is not possible. So how it will be lower boiling point? So that information is also enough to choose that this cannot be meta. Okay, and look at option 3, why it is not correct, because here molecule A, that is given para, but you are getting R from A, which is lower boiling point, and that must be ortho. So molecule A cannot be para, it must be ortho. So this is ortho, this is para, molecule C, and B is completely different types of molecule because it is 2D. It is not giving you any diazonium ion. It is that is reacting with Hinsberg reagent, and we are seeing the observation that it is insoluble in alkali, and that information is actually the indication it is 2 degree M. So this is the correct option. Correct statement we have to find about the given chemical reaction. What chemical reaction given? We have aniline in presence of nitrating mixture HNO3 H2SO4. We are getting para product, meta product, ortho product. What are the percentage? That is not mentioned. Now look at the statement. The first statement is saying NH2 group is ortho and para directive. Now that is true. And it is also saying as it is ortho and para directive, product B is not possible. Now product D is basically meta. But remember, in today's the first slide that we have seen, meta is also possible, and meta is basically it will produce 47%. So very significant amount. And why it is possible? It is possible because of this anilinium ion. And why this anilinium ion is formed? It is because of this acidic condition that you are using in this reaction. So NH2, in some NH2 group, I mean in some aniline molecules, NH2 group will remain in protonated form, and that is anilinium ion. And once it is anilinium ion, now the resonance is restricted. Now we cannot say that it is orthopara orienting. Okay, and that is the reason now there will be meta product also. So we cannot say product B is not possible. it will also be produced. So this is not correct statement and not obviously the correct option. Second statement, reaction is possible and compound B will be the major product. Now it is saying that meta will be the major product, but actually meta is not the major product, though it is significant, but it is not major, it is the second major. This is also not correct. Third statement, the reaction will form sulfonated product instead of nitration. This is completely wrong because we do not get sulfonated product. You get sulfonated product only when you use only H2SO4. But when you are using mixture of HNO3 H2SO4, it is not that you are getting sulfonated. So this is also not correct. Only one statement is left, which is the last one. It is saying reaction is possible and compound A will be the major product. That means the para will be basically the major product. And this statement for this reaction is actually correct. Fine. So this will be the correct option. And this para, it is actually formed in around, though it is already shown, still I am writing 41. This is 47%. And the ortho is very low, which is 2% only. The major product Z obtained in the following reaction scheme. The starting material is metabromoaniline. Then you are using diazotization reagent. That means NH2 group will be converted to N2 plus Cl minus like this. Then you are using, this is molecule X. Next you are using Cu2Br2. And we know diazonium salt, in presence of this type of reagent, it may be written as CuBr also. Then also same thing. So this type of reagent, you are getting Y. So now it is converted to Br. That means N2 plus Cl minus will be converted to Br. So 2 Br groups. And then finally, you are using nitrogen mixture and you are getting Z. So you have to recognize the molecule Z. Now, as it is diazotization first, and then you are using Cu2Br2. Molecule Y, it should be 1,3-dibromobenzene or meta-dibromobenzene. And bromine, that is halogen, when they are attached to benzene ring, I am writing X. This X may be ClBr. They are basically orthopara orienting. And as it is orthopara orienting, so obviously from the nitrating mixture, the electrophile that will be generated, this is electrophilic substitution, and the electrophile that will be generated is NO2 plus. HNO3, H2SO4 mixture, this is nitrating mixture, it will produce the electrophile NO2 plus, and this bromine is orthopara orienting. Now if it is orthopara orienting, then NO2 should be inserted at ortho position with respect to bromine, or it may be at meta position. Now if you look at molecule 4, here NO2 group at meta with respect to both Br, but this is not possible. Then option 3 also, here we have another problem. In option 3, if you see, NO2 group, its position is obviously ortho both with respect to this Br, and if you consider this NO2, it is para with respect to one bromine and ortho with respect to another bromine. So this is also possible, but the problem is 2 NO2 group will not be inserted. Only one NO2 group will be inserted. So that is why this should not be the correct option. Now look at this reaction. So this is molecule X. Next, N2 plus Cl minus in presence of Cu2Br2, which is Sandmeyer reaction, it will be converted to 1,3-dibromobenzene because N2 plus Cl minus is converted to Br. And as I have said, Br is orthopara oriented. So the next NO2 group, these two we have already cancelled with logic, proper logic. You are stuck between 1 and 2. If you are asking why not this molecule is possible. Now this is not correct option because if you look at this molecule and if you look at the option 2 molecule, this is containing 3 groups, 1, 2, 3 position. So this is from steric point of view, though its formation is possible because Br is orthopara orienting and this NO2 group is ortho with respect to both Br. From that logic it is possible, but steric point of view is the problem. If you consider steric point of view, it is not possible. Now look at option 2. This NO2 is ortho with respect to this bromine, but it is para to this bromine. That means that factor is fulfilled. Steric problem is also not high. You can also write the NO2 group in this position. Actually, it will produce same molecule. So that is the reason option 2 should be the correct option. considering all the logic. Consider the following reaction. Starting material P. First reaction NaNO2HCl, that is diazotization we are doing, and then you are treating it with beta naphthol, basic condition. We know this test is basically dye test. Colored solid, highly extended conjugation product is formed, and that is the reason it has intense color. And the next reagent that you are using for another reaction, Br2 water. Remember, bromine water, when we use with aniline, then we get substituted product. I mean, suppose you have taken aniline, you are treating it with bromine water. In today's just we have discussed this. So these three position there will be bromine. So it is matching with this formula, tribromine. So compound P, it must be aromatic amine, right? But it is not simply aniline, because if it is simply aniline, then total number of carbon must be 6. And only aniline, that option obviously not present. So it is C7 and methyl group is present. Now if we look at the options, here try substitution of bromine, that means ortho and para position with respect to the NH2 group, that must be empty. Otherwise, how 3 bromine will be inserted? Because only ortho para hydrogens can be replaced by Br. You cannot replace meta hydrogen. That means this extra carbon which is present as methyl group, obviously it is present at methyl group, which is clear from the options. In all the options you will find some methyl group, para position, meta position, ortho position. In option 2 it is not just ortho, it is ortho also attached here. But in this case option 2 if you consider, then this bromination product is there, the formula should be C8, total number of carbon 8, and this is not possible. And also as you are doing diazotization, that means it must be 1 degree, but this is 2 degree. So this cannot be at all correct option. Now among 1, 3, 4, 1 and 4 not possible, because the bromination product ortho para position must be vacant, right? So that is why now we are left with only option 3. Now look at this, when you are doing diazotization, you are getting N2 plus Cl minus, rest of the part no change, then there is, you are treating it with beta naphthol, and you get the diazotization product, this one. And when you are treating it with bromine water, these 3 position, I mean 2 ortho position, para position, all these 3 hydrogens now replaced with Br. So the starting material, it must have, that is NH2CH3, they must have at 1 and 3 position meta. It cannot be ortho or para. And as it cannot be ortho and para, these 2 options cannot be correct. Option 3 is the correct option. An amine on reaction with benzene sulfonyl chloride, PHSO2Cl, produces a compound insoluble in alkaline solution. Remember, this reagent PHSO2Cl is known as Hinsberg reagent, which helps us to understand, to distinguish basically 1 degree, 2 degree, 3 degree amine. And when it is saying it is insoluble in alkaline solution, it is the indication that it is 2 degree amine. Because when it is 1 degree amine, it will be soluble, and for 3 degree there is no such reaction. This is the first information. The second information is this amine can be prepared by ammonolysis of ethyl chloride. Ethyl chloride means ethyl group, then Cl. So this information proves there must be ethyl group attached to nitrogen. This is 2 degree. Obviously the format should be like this, RNH, R prime, if both the groups are not same. So one of the R group, it must be Et. Now if it is so, first of all, it must be 2 degree. Second thing, there must be one Et directly attached to N. If you simply consider these 2 logic, this is 2 degree, this is 1 degree, obviously not correct. This is also 2 degree, and this is 2 degree. Now among these 3 2 degree, option 2 already cancelled because it cannot give insoluble, it cannot be in producing compound with PHSO2Cl which is insoluble in alkaline. So that is why it is not possible. But we have 3 types of 2 degree. But in 3 types of 2 degree, look at the first 2 degree, you have propyl group, but there must be ET group. Then option 3, that is also 2 degree, but there is propyl group, methyl group, no ET. Only in last molecule you have propyl group and ethyl group. So this should be the correct option. So when it is 1 degree amine in presence of PHSO2Cl Hinsberg reagent, you get this type of molecule where still one hydrogen is attached to nitrogen, which is responsible for the solubility in alkaline medium. But when it is 2 degree amine, you do not have any H attached to N and it is insoluble in alkali. This is Hinsberg reagent test. And next, you are doing ammonolysis. So the final molecule should be like this. On one side there is ET, another side there is propyl group, and it is matching with option 4. And as you are getting this by ammonolysis of ethyl chloride, so the starting material should be something like this: 3 carbon chain, then NH2 in presence of ETCl, or in general you can consider RX. The lone pair is attacking the alkyl group. You are getting finally ammonolysis product, because this ammonolysis reaction, remember, it is already discussed. You can also check that particular slide how it happens. So here the logic is it has to be 2 degree amine, because on reaction with PHSO2Cl it gives water insoluble product. And the second thing, as you are getting it by the ammonolysis of ethyl chloride, so one of the group must be ethyl. So the type should be like this, as I have mentioned here. It should be R group, and group may be anything that is not clearly mentioned, but NH and ET. Okay, so this is the format of 2 degree, but one of the R group must be ethyl. Then only it is matching with all the information that are given in the question. So correct option, option 4. What is the correct sequence of reagent used for converting nitrobenzene into meta-nitro-dibromobenzene? So starting material nitrobenzene, final product like this, and you have to use total 4 reagent. Number 1 step, second step, third step, fourth step. Fine. Now if you look at these options, different reagents are there, but different sequence. Now NO2 group is no longer present in the final molecule. That means you have to remove it somehow, and if you convert it to NH2 group, and then if you do diazotization, then diazonium salt, if you treat with CuBr, it will be, or bromine, it will be converted to what? It will be converted to bromine, right? So that is why obviously first you have to convert it to NH2 group. Now when you are converting to NH2 group, there must be some reducing agent, and reducing agent in the first step you have to use. So from that logic, you cannot use option 1 and 2 because you do not have any CH2 group, right? In the first option it is used NaNO2, but NaNO2 cannot be used on nitrogen, it must be aniline. Then this is also not correct because you are not getting NH2, there will be bromination simply of nitrogen. But option 3 and 4 you are using some reducing agent, and reducing agent will help to convert NO2 to NH2. And once it is converted to like this, next what you can do, sorry, what I mentioned, it should be bromine and Fe first, because if you have already converted to N2 plus Cl minus, that is if you use first reducing agent, the problem is it will be converted to NH2. But remember, in the final product, there are 2 bromine. One bromine you can get from N2 plus Cl minus, but other bromine must be coming from some bromination agent. So that is why first we are doing this bromination of nitrobenzene. Nitro is para orienting group, so Br is inserted meta. And look at these 2 positions of final product. These 2 are 1 and 3 positions. That means first you have to insert this meta Br, and that is possible only with nitrobenzene. So that is why we are using bromine Fe first, then reducing agent. And this reducing agent is converting NO2 group to NH2, rest of the part no change. Then diazotization, N2 plus Cl minus, and finally Q plus bromide, and N2 plus Cl minus is converted to Br. So in this sequence, if we follow, which is matching with option 2, then we can get the final product. Okay, so this will be the final question. We are at the end of the session. Thank you for listening.